kan vi ta det när de kommer.
Ja, men vad ska vi för? Du har betalat det.
Ja.
Vad var frakten?
Frakten var 59 så 20 ja.
Och nu var det 2,29.
Ja, jag tror det.
Okay, I think the stream is actually started already. So, welcome to this course that you already started on and had a number of lectures with Morgan, but now it's time for me to take over and talk about some of the layers that are a little bit higher in the protocol stack. So, as see, today we'll talk about internet routing, and then later on we'll talk about things like performance in network, how to calculate that or how to look at that, quality of service, software-defined networking, and some other things related to a little bit more higher up. But today we have a lecture in Växjö on Monday, and that will be streamed as well for you in Kalmar here. So I will be on Mondays in Växjö and Thursdays here in Kalmar. That's the plan. The fourth assignment, I know that you're still struggling with the third, or some of you maybe the second assignment, but there will be a fourth assignment, and that will be connected to the lecture today mainly on routing. I will publish some parts of it at least quite soon, and that is the part on how to set up an environment, how to run it, because you will run it in a network simulator called GSN3. And as I mentioned already in the beginning of the course, it requires some support, hardware support, in order to actually run. So I want you to install it as soon as possible and make sure that you have a computer that works for it. And then probably next week sometime I will publish the actual assignment as well. But let's move on then to the lecture today on routing. So see, we'll talk about aspects like different routing protocols and also especially what's called multicast routing, which is a little bit more tricky. But first we'll go back a little bit and talk about things that I know Morgan already talked about. We have a network, and in that network we have a number of nodes. Earlier you just talked about network nodes and that you can connect different parts of a network through these nodes. And then we said that in that network we have these two different aspects, forwarding and routing. Forwarding is just we get an input and a packet coming in onto one of these nodes, and we need to forward it somewhere in the network. And that is done in what we call the data plane of a node. And then we have routing, and routing is how to decide on where that packet should go. And it's a bit of confusion because when we talk about the equipment that we use for this, we normally call them routers then. We have a number of routers, we connect different networks to them, but the main task that the router is doing is actually forwarding them, because it's forwarding that it's doing all the time, except packets on different input interfaces, and then we forward it to some output interface. So forwarding is what we do all the time, and routing we do now and then, depending on what type of routing protocol we're using, what type of routing strategy we're using. But routing is then when we decide on how to forward packets in the future. We have two forms of routing then. We have a static routing and dynamic routing. So static routing means that we always route in the same way. We have a table saying that, okay, a packet coming in that is supposed to be sent to a certain network, we always send it on the same output interface. And that table is initiated when we boot a system typically, or manually changes some state. But otherwise, we have dynamic routing, which we normally talk about as routing then, when we are continuously updating this routing table. dependent on what goes on in the network. And what can happen? Well, it can happen that suddenly we have a new network available, or we can see that there is a problem in part of a network. We have congestion, so it's a very slow part of a network. We may want to try to route around that problem, or there can be links that is down, hardware that is cut or whatever. So we need to continuously see what is going on in the network and adjust our routing table so we are efficiently forwarding packets. Static routing is done by normal hosts. So any host that connects to the network need to know where to send packets, and that is typically done with static routing. You could also have normal hosts actually take part of dynamic routing, but that's quite rare. Normally we do static routing. And if we do that, we typically have only these two enters then. The local network, well, that is the network that we are already in. Now we're talking typically about a logical network. We are in the logical network. And how do we know what the logical network is? If you think about an IP network, what is the logical network here? Anyone? How do we know if the destination is in the same network as the source? Because that would be the local network then. Well, we have to look first at the address, of course, but we also have to look at the network mask to know if we are in the same network, logical network or not. And Morgan talked about there are different ways to actually allocate these networks. We can use it with the old class-full addressing, the class A, B, and C networks, where we know that for a class C network, for instance, we have these 4 groups of numbers, and the last group is for the host ID. And then we know that all these 255 addresses or 556 are in the same address or same network. So as long as we are in the same network, we have direct delivery. We know that, okay, we are close to each other, we can make a direct delivery. But there is still a complication, of course, because the IP address is not what we use in order to actually deliver on the physical network, right? What type of address are we using for the actual delivery of a physical network? Yeah, MAC address. So we have an Ethernet MAC address, for instance. And how do you find the MAC address of a destination? We use another protocol, the ARP protocol, Address Resolution Protocol, that helps us to translate from an IP address to a MAC address. So that's what happens if we have local network. We are in the same network. We see that, okay, the recipient is in our local network. Then we just need to find our MAC address, and then we can actually send it directly. But then we have the next entry, default entry. In all other cases, we cannot make a direct delivery because the recipient is not in our network, is somewhere else on the internet. What do you do then? Well, then we send it to the nearest router. We just leave that problem onto the router and say, okay, here's a packet, deliver it for us. But also in this case, the nearest router in our routing table typically looks like this. So here we have an example. We have a small network with a number of hosts in it. We have a router. We see that in this example we have an Ethernet network. It's actually a class B network. We have 16 bits for the host ID. So we can see that we have 16 bits here. That means the 2 last groups here will be for the host ID. when we look in our routing table now, we see that anytime we want to send to someone in 128.10. anything, because that is what our mask tells us, that anything on the last two groups here will be in the local network, then we can make a direct delivery. So then we find the MAC address and then send it from one computer here directly to the other computer, for instance. But if you want to send to someone out here, then we get to the next row here, the default row. And then the mask is here because it covers everything. What we do then is we send to the router, which means that the router needs to have its own IP address, so we can actually find it. So in this case, the router has the local address 100 then, so that is where we send it. But again, of course, to actually deliver the packet, we still need to have the MAC address. So now we have to find the MAC address for the router interface here, and then we can send it to the router. And when it reaches the router, well, then it's up to the router to handle the problem of finding a path for it. And in the router, we probably use dynamic routing then. So there's a software running on the router who is maintaining the routing table, making sure that it's correct and adapts to any changes in the environment. And to do that, we need information, of course, about the environment, and we get that from other routers in our neighborhood. So continuously we exchange information with other routers in our neighborhood, and based on that information what we get from them, we calculate a new routing table. And that's called then a routing propagation protocol, or just a routing protocol. So here we see that we have two routers now. They are connected with a common net, called net 1 here, and they each have its own private network, net 2 and net 3. Now, if we start up with this situation, R1 and R2 knows about their own networks, of course, because they are configured to handle net 1, net 2 and net 3 here. But then we have a common network, and they also know about that one, but they may not know what is beyond that network, net 1. So in order for anything to happen here, the routers here, R1 and R2, need to send out the information to other routers that, okay, now I exist in the network and I can actually deliver packets to these net 2 and net 3. And before that has happened, we couldn't get any traffic to or from net 2 and net 3. So we talk about that a router is advertising whatever is behind the router. And before we have advertised it to other routers, we couldn't start communicating. I think that's probably much what we're saying here. We use incoming information to update, yeah. So now is the question then, who should we communicate with? I mean, we have our router. There will be other routers out there that we need to communicate with in order to advertise routes and get the information about other networks so we can start sending. But what router should we communicate with? Well, if we look at internet, there are millions of routers out there supporting millions of networks. It seems a little bit tough that when we put our router on the network that it has to start communicating with all the other routers on the internet to handle the propagation of network. So that's not how we do it. Instead, we introduce this concept of an autonomous system. So autonomous system is, as you see, a network of, well, a set of networks and routers under one, what we call administrative authority. So someone that actually have control over these networks and routers and can decide on how they should work. But there's no real definition on how big it is. So autonomous system could be just our house. We have one router and we have some some computers. We could define that as an autonomous system. Or it can be a company with a number of computers and possibly a couple of routers. Or it can be a big company that have several different sites in different countries, but are still seen as one logical autonomous system. So the size doesn't really matter. The important thing is that someone is in control over all the devices here. They can decide how it should work. So within this autonomous system then, we decide on how routing should be handled within that autonomous system. And within that autonomous system, we typically communicate with other routers then. That means now that we have two different levels, because we have all the routers within an autonomous system, and then we have another autonomous system, and the third one. And if you think about the number of organizations out there, we probably have hundreds of thousands or millions of autonomous systems then. For each of these, we need to decide on how to handle routing. But we also need to decide on how to be able to send traffic between them. Because now we have two different levels of routing. And that means we have what we call interior gateway protocols for the interior of an autonomous system, how to handle routing within that. And then we have exterior gateway protocols that decide how routing should be done between autonomous systems. And we will look at routing protocol belonging on these two different types of situations then. So here we see a simple example then. We have two autonomous systems here. In the first one, we have a number of routers, R1, R2, R3, that are connected somehow. And then we have another autonomous system with a number of routers. Each one can decide separately how to handle routing within the autonomous system. But as soon as we want to communicate with someone else, we need to define what we call border routers. So in this figure then, with R1 and R4 are border routers. They are both communicating internally with other routers, but they also have connection with other autonomous systems using an Igmp protocol. What is an optimal route? What is the best way between two different computers? Well, that is probably what we would like to have. I mean, when we send a packet, we would like it to take the best path. But the problem is that we have different requirements depending on the type of traffic. So it's very hard to say what is the best path, what is the optimal path. And we can see down here we talk about different types of applications. So for remote desktop, for instance, where we push a key and that key is sent to the other side and then we get a reply back. So we have an SSH or terminal connection. Well, in that case, delay is probably very important. We have very little traffic. It's only a number of characters per second, perhaps. So that's not very important. But that the delay is low is very important. Otherwise, it will be very hard to control that other site. For a browser, web browser, here capacity is more important because we are downloading large files. It has to be quick. But then delay maybe is not as important. It doesn't matter if it takes 0.1 or 0.2 seconds to get the file. The important thing is that we get it quickly. We don't have to wait 5 minutes for the file to download completely. We want to have it within a second. And then, for instance, for real-time audio, if we have listened to a radio stream, for instance, jitter is another property that is important that we'll talk about later on, but that is variation in delay. That is something we would like to have. So different applications have different requirements. That means that we couldn't really say what is optimum in general. But a router needs to decide on some path. So the question is, which one should it show? Yep.
Question about border routers. Do we always have one in one system, or do we have?
You need to have at least one, but you can have several border routes as well. So big organizations typically have several ways to go out and reach other parts of internet. Yeah. If we only have one possible path, then it's not a problem, of course. Then we have to choose that one. And that is true for most homes and small campuses. We have one connection out to internet, and that is the path we have to take, of course. But if you go into internet, we see that there are often many possible ways to go. So then it's interesting to see what is optimal then. But in order to try to talk about what is better than something else, we need to be able to measure it somehow. And that is done with what we call a routing metric. It's a way that we can put a number on different parts of a path in order to decide which one is best. And we can use many different input to calculate the metric. Let's see, we can use throughput, for instance. Throughput is then the number of bits per second that we can push through the network. The more the better. So we have, well, depending on if we try to minimize or maximize the metric, often we try to minimize. And then throughput would be, the highest throughput would be 0, and then it goes up the slower the network would be. Delay, the same then. We probably want a low delay. So the higher the delay, the higher the number. Jitter, as I said, variation in delay. We can measure that and put a number. The more variation, the worse. But there are other possible metrics as well. The one that is very often used are these we talk about here: administrative cost and hop count. Administrative cost is just a cost that we say. We assign a number to a link. And that is typically when we design the network, we decide that we would like traffic to go through a certain part of a network rather than another part of a network. And then we put an administrative cost that is lower in that part. So when the routing protocol runs, it sees that this is a cheaper way, and it will choose that one. Why would we want to do that? Well, it could be that we would like to route traffic through part of a network, so the other part of a network is available for some special traffic. Or it can be that the cost we have to pay to use different links are different. So then we decide that the cheaper link have a lower administrative cost. And then we have a hop count. And hop count is just the number of links that you choose. Each time we pass a router, we have to make a hop in order to get to the next network, and then we hop from one network to another. We can easily count how many hop we do. You probably done that already in the assignments, right? How to calculate the number of hops you have. There is a tool to do that. You don't recognize that? Traceroute, exactly. With traceroute, you see what different parts, what routers you will pass from a source to destination. So that's exactly that. So if we now think about, okay, we have many different metrics. We can choose different ways to allocate a cost to each network we have to pass through or each link. So the question, what should we use? Well, the idea is that within an administrative system, we choose something. But we have to choose just one metric, because otherwise we couldn't compare different parts of a network with each other. And since we have control over our own administrative system, it's up to us to decide what we use. So we can freely choose that. If we now connect several administrative systems together, we will have a situation then that in different administrative systems we use different metrics because we have no control over it. Which means that when we start to try to look at metrics between administrative systems, we see that it will be very hard to compare them. Some systems use hop count, some systems use delay, and some use throughput. How can we calculate the cost entirely through all of these? It's impossible to find a way to compare them with each other. So for that reason, between autonomous systems, we don't use metrics at all. So Igp protocols that tries to find ways through administrative system doesn't even try to make it optimal. They just try to find a possible path. And the first path it finds is the one that it will choose. So optimal routing can only be performed within administrative systems. And here we see exactly like for normal routers within an administrative system that if we would like to have traffic flowing in, we need to advertise our administrative system to other administrative systems. So it's really the same thing here. But now it's not only one network, it's an entire administrative system that need to be advertised to the rest of internet. There are a number of specific routing protocols that we could choose from. And we will look at these: the border gateway protocol, the routing information protocol, open shortest path, and intermediate system. So these are actual protocols we look at. There are more than that. There are quite a few, but these are the ones that we'll take a deeper look at. And we'll start with the first one, the border gateway protocol. So border gateway protocol is an Igp protocol. That means it's routing between the autonomous systems. It has some properties as is here. First, policies to control routes advertised, which means that when we advertise possible ways to use our autonomous system, our autonomous system already has connection to some other autonomous systems. When we connect to a new autonomous system, we can say that, okay, I have connection to autonomous system 3, 4, and 5 here. You can send traffic to number 3 and 4 through my network, but network 5 is not available for you. I will not help you route traffic to that one. So that's the type of policy we can say. We are willing to forward traffic to other parts of the internet, but not all parts, possibly. The information we send between the routers here are using TCP, so it's a reliable transport. What it gives, as I said before, is a path of autonomous system for each destination. So say that we would like to send a packet to the White House in United States. To reach that, we probably need to go through several autonomous systems. First, we have here at the university, which is part of SUNET, which is one autonomous system. That one is connected to Nordinet, which is another autonomous system, and that one is connected to some American network provider, which have its own autonomous system, and then it connects to the White House, who the government, United States, who have their own. So at least 3 or 4 different autonomous systems we have to go through in order to reach that. Within each of these autonomous systems, there might be several routers. But when we route using Igp, we're not interested on the details within the autonomous system. We only know that we have to go through first autonomous system 1, and then 3, and then 5, and then 7. And now we can reach the server we wanted to reach. The details of that is really up to each autonomous system. So what we give here is we're giving a path of autonomous system that makes it possible to reach that host. But we don't know exactly which routers will pass. This BGP is the protocol that is used on internet today, and it has been used for a long time actually. So all routing between autonomous systems on internet is using BGP. Currently version is, as you see, version 4. That's since 1994. Before that we had earlier versions of BGP that was used for internet. So BGP has really been the only protocol that has ever been used when we talk about the internet as we think of it today. So it's quite on its own here. There are some other protocols that are proposed as exterior gateway protocols, but none have had a chance really to be chosen. And it will be very hard to change that, because the entire internet is now built with this protocol. To change it would require, well, it would be very hard to do that. We would probably have to shut down the internet for a day or so in order to make it happen. And no one wants to do that. BGP supports classless inter-domain routing and use what we call route aggregation. We combine many different networks in one entry in the routing table to decrease the size of the routing table, because that is an issue on routers on this level. If you want to connect your administrator system to internet, you probably couldn't support the entire routing table for internet because it's too big. So you only support part of it, which means that you couldn't directly connect to all parts of internet. You have to, some of the traffic you just pass on to another network provider who can handle it for you. There are only a few number of routers at the top level of internet that actually have an entire routing table for internet and can support it. But we'll see that actually, because we can look at the size of these routing tables. I checked the numbers today, and as you see today, the routing table for IP version 4 contains approximately 820,000 is the number today, 650,000 were last year. So there are roughly 820,000 different autonomous systems then on internet for IP version 4. And for IP version 6, it's much lower, 82,000 currently, so just 10% of IP version 4. However, IP version 6 is growing much more rapidly. And why is that the case? Why doesn't IP4 grow anymore? It can't. No, it can't, because we have run out of IP4 addresses. So in principle, all IP version 4 addresses are already allocated. There are ways to split them, which would give us 2 entries. So they can still grow a little bit. And there are some that are allocated but not used. So it's only when they're actually used that they will appear in the routing table. But it couldn't really grow much more, because we run out of them. So IP version 6 is an option, and here we have lots of space to grow in still. I mean, we only have 10% of IP version 4, but the address space is huge compared to IP version 4, so there's no risk of running out of addresses for IP version 6 for a long time. Now, I mentioned the backbone of the internet, these routers at the top that need to know about all the details of internet and to handle all of these, the entire routing table. And the backbone consists of what we call these tier 1 operators. And they are not very many, as you see. About 15 in the world. So they are actually creating what we call the backbone of the internet today. We have one of them here in Sweden. Telia Sonera is one of its tier 1. Otherwise, most of them are in the United States, but there are a few in other places as well. What they are doing is that they take upon themselves to actually handle the entire routing table and to freely forward traffic to all the other tier 1 operators. And everyone else needs to have some type of relation to at least one of them in order to be able to connect to internet. So this is what Telia Sonera's network looked like a couple of years ago at least. So we can see that they have lots of nodes in Europe, and they have some in the United States, and then they just have a few more in the world. So obviously Telia Sonera doesn't cover the entire world. But they have connection to all the other tier 1 operators, which means that they can forward traffic to any part of the world by sending it to some of the other. We can see one of others. We have NTT, which is then in Japan. And we can see that they have, of course, much better connection in Asia. They have lots of links to United States and some nodes here, and they also have some nodes in Europe. But of course, their strong point is Asia, Southeast Asia. So that's how it works. The different tier 1 operators, they cover different parts of the world. They are overlapping more or less, but all of them someone is covering each place. So there is a competition between them, but they're also helping each other. And if you look at this structure then, we have a tier 1 operators here at the top. They are connecting to each other, and then they connect to different network service providers, one level below. And one level below, for instance, we have Nordnet, Sunet. They are one level below these tier 1 operators. And then below that we have different regional ISPs, but they could cover a country or a couple of countries or just part of a country, but it's a region, they are not worldwide. And then below that we can have different local internet service providers. Like in Växjö we have Griffeldata and we have Växnet and so on, local ISPs. There are lots of them all over the place. What you have here in Kalmar, you have some local ISP here, I guess. You don't know? There have to be some, or several probably. Yeah, Telenor probably offers services, but they are more on a national level then, of course. But yeah, they offer local as well, probably. Yeah. So that's border gateway protocol and how we build up and structure an entire world with BGP connecting different administrator systems. And as long as we have connection to one of these internet service providers, then they in turn have connections with other ones. So as long as we can get connection to one of them, we can reach anyone in the world. That is how it works. And typically, at the same level here, in this figure here, the operators have agreements, so they are connecting to each other and they share traffic without paying any money. So they are just freely sharing traffic with each other. But if you go down one level here, the one below here have to pay to the people above in order to connect, to have network access. So that's typically how it works. But you can also make shortcuts here. For instance, two regional ISPs can decide that, well, instead of having traffic in Kalmar where we have maybe the two different local ISP, instead of them both sending their traffic up to a regional ISP in Stockholm perhaps, before you can send between two computers here, they could have direct connection between them. So these are the policies that we can set up for routing between autonomous systems. They can say that, well, I accept traffic from you as long as it doesn't go to another autonomous status, so it just stays here. So we can have shortcuts in the communication here. Right, so that's BGP, Border Gateway Protocol. Now we'll move on to the other routing protocols. As I said, BGP is the only one that we'll talk about as exterior, which means that the rest are interior gateway protocols then. So this is the RIP, the Routing Information Protocols, is the first one. It has a metric, which is hop count, which means each time we pass a router, we increase the cost with 1. It uses UDP whenever routers are communicating with each other to decide for the best paths. There are two versions, I see version 1 and version 2. Version 2 added the possible, it's actually more than that, but among things that was added was to use multicast instead of broadcast when we are exchanging information between routers. The difference is, of course, that broadcast is heavy on the network. If you send a broadcast message on the network, everyone on the network have to react on it. If you send a multicast message, only ones that subscribe to that multicast address actually react to it. So it lowers the burden on the host of the network. RIP uses distance vector algorithm. I know that Morgan also talked about this before. When we're looking at how to find a path through a network, we have two main options. We have a distance vector and they have a link state protocol. RIP is using then the distance vector, which means that in order to decide on a path for our traffic, we need to know what other routers know about the network. So we exchange information by sending each other our current version of our routing table. And based on that information, we update our own routing table. So distance vector means that we always exchange information with our neighbors, but not with routers that are further down the network. We will look at some example here later on. RIP can propagate the default route, and that can be useful, for instance, if we have a large network, we might have several exit points, several boardway routers, and RIP can then forward a default route so we know which one we should take. And the other one could be reserved, and that we only use if the first one fails. RIP is implemented with this Unix program routed, which is supported by all Unix distribution, which means that actually hosts running Unix can take part in routing. But normally they do it in a passive way then, so they don't try to start routing. They only listen and update their own table based on the information that they see in the network. This is the packet format that RIP is using. And let's see if I can get one. Yeah, here we are. So we start with a command first. And there are just a few commands possible. It can be just that this is an update, or this is actually routing, or it can be an authentication. There are a few things we can do, but normally it's just that this is my routing table. That's normally what we say here. And then we have version, and version is then 1 or 2, the version of RIP. Then we have the field that's called as the family of net. And if you look down below here, you see that normally it says 2 here. And 2 means that it's IP routing we are doing. RIP can actually support other types of routing as well, not only for IP networks, but other networks. And then we use different numbers here for different networks. Could be AppleTalk or DECnet or so on that old. Not used much today, but RIP supports it. If it says FFF here instead in family of nets, you see, then it says it's the information that comes after here, it's actually authentication. So we can authenticate from one router to another and say that, okay, I'm this one and I know this password here. That's the way to increase the security. Otherwise, it's easy to set up a router, what they call a rogue router in the network, who starts sending RIP packages and poison the information in other routers by sending in false information, making people route traffic wrongly and so on. But by using this possibility to authenticate, we can at least make it harder to do that. But then we have the main part actually of what we're sending. You see IP address of net 1, subnet mask of net 1, next hop for net 1, and distance to net 1. This is really information for one entry in our routing table. So what we say is that to reach a certain network with a certain subnet mask, there is a distance for us to reach that. Could be 3-4 hops away, for instance. And to do that, we go through and then we say what the next hop is, where we send the packet in order to do that. So that's all the 4 lines here for one entry in our routing table. And then we just take the next entry in our routing table, and that will be the next number of lines here. And then it continues for as many rows that we have in our routing table. So essentially that is what we're sending to another router, our current routing table. So that is our view of the world right now. We know that we can reach these networks. There's a certain cost of reaching each of them, and we tell them how we reach them. This information is sent to our neighbors, and our neighbors now, with distance vector protocol, compare this information to see, okay, I can also reach network X here. My cost of reaching that is maybe 5, and now suddenly I get a message from another neighbor here that I can reach that network with a cost 2, which means that, okay, that means it's better for me to start sending my packets to him instead, because now that will be cheaper than before. So I update my routing table. So that's how distance vector is working. Okay, before we take a break here, any questions about RIP? Right, okay, so let's take a 10-minute break then.
det är inte...
Ska du trycka upp något annat i Slack-channen?
Nej, inget. Det var någon assignment-fråga tror jag.
Ja.
Uppsala. Så det Jo, vi borde få dem imorgon. Jag menar om den är skickad så åker, alltså det är DHL, så det är inte Boston.
Ja, DHL,
De kommer, jag beställde den här labbagrejen. Beställde från från Nederländerna. Jag fick den dagen efter.
Ja, jag vet, alltså jag beställde
Jag fattar inte, jag fattar inte hur.
Många gånger DHL, det kommer nästan där.
Hur? Det är helt sjukt.
Jag hade ett paket som jag beställde på Sidon. Men den skickades från Spanien. Så jag kunde följa den. Sen till slut så stod det, det har kommit till mottagningsstället. Inte lämningsstället. Inte på någon markering heller. Gick på Fänkes hemsida. De har någon chattbot. Så man kunde fråga han.
Ordernummer, kollinummer.
Kollinummer, utan 201. Och sen får man
Veta vad den är.
Så gick jag igår och testade. Det finns inte här. Gå och kolla in så jag visar henne. Ja, jag hittade den på golvet.
Oh my god. Har du kommit någon vart med så? Vi fick mycket tankar med. Den här image var det lite...
Vi har ett nytt så jag kommer troligtvis sitta ikväll.
Kan inte, alltså jag kan inte till klar med den här, jag kan sen efter det har vi...
Men jag har de 3 som skötas, man vet.
Ja, men då har jag också va? Du ska inte bara ha vad du som rätt.
Ja, men jag tror inte att du har några att signa till. För att jag tror att Sinisha tog några.
Ja men de vi skulle göra.
Ja,
från början 9.
Nej, han skrev 7 till slut. Men jag hittade inte stycken. Kolla själv. Hittade någon fulldag.
Jag har fortfarande
jag tog 3. En av dem kommer inte rätta på grund av han har en paket.
Ja.
Så jag kommer...
det var bara...
Jag kan inte sitta och skapa paket själv och... Eller kolla igenom vad som tillhör vad.
Nu är det faktiskt dags. Hallå? Jag är i skolan. När snart?
Han sa att det skulle vara så snabbt.
Ja, men ringa då.
Skönt att det är skönt att de inte
Ja, ni kommer till universitet ska hemma först. Ja, bra.
Så jag kollade igår. Jag visste inte riktigt så jag beställde. Det måste vara det.
Är det svårt? Eller? Nej, jag tänkte det här. Så vi går igenom nu. Ja. Vad tog det? Det var väldigt många Rubriks Kuba-frågor.
Det är ju 7.
Är det någon tävling eller?
Hade du med dig nu?
Jag brukar ha med mig.
Ja.
Sen var det just för.
Fast jag såg en YouTube-video om det. Det var någon ganska lång kille som körde, just det gjorde han ju. Han jonglerade med 3 stycken Rubriks Kuba och löste dem under tid.
Jag har sett den också, det går ju skit. Alltså han löser på 20 sekunder.
Alltså det där är ju bara sjukt. Alltså det är ju liksom...
Jag funderar på om den videon är baklänges.
Ja, att han har...
Ja, det är imponerande. måste kasta dem så att han fångar dem på ett sätt så att han kan
Ja,
vrida
exakt.
dem
Alltså
in i
planera
handen.
kastet i alla fall.
Ja.
Så att,
Så att den landar på rätt sätt.
ja,
Mm.
nej,
Jag har sett en video med en när han kastar en och löser den.
Okej.
Men 3 då är det...
Med en hand var då alltså? Eller vadå?
Ja.
Mm.
Jag tycker de som läser ögonbindel är sjuka också. Som memorerar. Men det måste ju typ de som gör det ute också. De måste ju typ memorera.
ja, vad hinner man se? Alltså vilken av kuberna ska man kolla följa liksom?
Jag kan knappt jonglera med 2 bollar.
Nej, det är ju så från de spelar schack också. Simultanschack med kanske 10 olika samtidigt. Och bara ha allting i huvudet. Eller liksom hela, alla ställningar.
Ja, det var...
Ja.
Hade du beställt några nya kuber? Är det vanligt för att
Nej, det är den jag saknar.
Jag har beställt en 3 gånger.
Magnetisk.
Magnetisk, ja.
Blev beställt idag då?
Ja, jag beställde det när jag kom hem.
Vadå? Nu har jag redan skickat.
Beställt en 4x4 sen.
Ja, vi avancerar nu.
Alltså jag har hur mycket sen.
Ja.
4 gånger 4 är fan inte så när man väl... Alltså det
Nej,
tog ju
den är bara
bara 2
rolig,
veckor att
alltså,
lära sig.
Den är roligare än den här. Alltså,
Ja, 3 känns ju mesig än 4.
det där känns som ett äventyr när man börjar med den.
Jag
Alltså,
börjar mönster på min 4 nu, så jag gör diagonaler istället för att
Ja.
läsa sidorna.
ja. Nej, 4 gånger 4 är nice.
Funderar på att beställa megabit.
Ja, de är roliga. Men typ första dagarna, sen blir den tråkig för att det är som en 3 gånger 3. Men de är riktigt roliga i början.
Får bara jonglera då, om det är tråkigt. Så.
Nej, jag tror det. Vet ni om det är tillåtet att använda den i Sverige? Ja, i tvåan. Inte bilden är för mycket. Om vi har, även om vi har rätt header och läser bilden som en fil, som vanligt.
Jag läser på Byte.
Ja,
In i en Byte över...
ja.
Så du använder en
Varför blir det? Ja. Nej,
Stoppar ni både header och image i den enda Ferrari då och skickar den?
Ja.
Ja.
Det var en som skrev släpp, men det var inte om det här.
Jag såg det. Okay, so let's
Ja, ni får.
continue then.
Ja, ni-
Moving on to the next interior gateway protocol, the open shortest path protocol. So still within an autonomous system, of course. Open shortest path is a little bit newer, which means that it can support these classless interdomain routing addresses and subnetting, which is VRIP only supports normal, simple subnetting. Here we can have authenticated message exchange all the time, so we can better support against different types of attacks. Again, we can import routes from outside, so we can know where to reach different parts of outside. So not only that we need to get out, but actually depend on where we go on the outside. we can see, okay, if we have several border routers, we can know which one we should take here. So we can have a little bit support for that. Open short path uses, as you see, link status instead of distance vector. And it also supports multi-access network, for instance, Ethernet, which is a multi-access network. We send and then we know that many listen to it. When RIP was developed, the normal network was only star networks or mesh networks. So all hosts were on single access lines, not multi-access. And that's simplificate if we have multi-access and use that. But the main difference, or one of the main differences, is that it uses link status instead of distance vector, which is normally much more efficient. So let's look a bit at link state. You already covered it, but we'll look at it a little bit again then. So in order to use link state here in an autonomous system, we look at networks and routers. Of course, that's what we have, and we have to turn that into a graph because link state works. It's a graph protocol. So routers corresponds to, as you see, nodes here in the graph, and the networks are the edges, the way to reach from one router to another. So it looks like this then. Here we see that R1 up to the left here is connected to two networks. The network up in the left part is not really seen in the graph because that is an end network. It doesn't reach anywhere, so we couldn't reach any other router through it, so we don't see it. But we see there is a network connecting R1 and R2, so in the graph we have an edge between R1 and R2. The same network, as you see, is used to connect between R1 and R3, so we have another edge between R1 and R3. So we have to look at the network as a graph here to run the protocol for link state. And what happens now is that adjacent pair routers periodically test the connectivity. So what they do is they really are sending a test packet. Can I still reach that other router that is also connected to the network? So again, if we look at this one, R1 would then periodically send a test to R2 and R3 to see, can I still reach these routers? And once we have got a reply back and see, yes, I can still reach them, then we broadcast this information to everyone else within the entire administrative system. So this is one of the main differences between distance vector, because in distance vector we only communicate with our neighbors. Here we communicate with everyone in the autonomous system. But what we send is just this information. Can I still reach that other router or not? In distance vector, we have to send our entire routing table. So it's quite a lot of information. Here we only send that status, reach that router or not, and possibly a metric connected to it. And then, at the same time, of course, as we do it, all the other routers doing the same thing, which means that we periodically will receive information from all the other routers in the network about what routes they can reach. That means that each router now can construct this graph here based on the current information in the network, which routers each other router can reach. And if we now put a metric also on the different links here, we can calculate the optimal path to each other part of a network. So that's what we do for the link status protocol then. Now, if the network grows, if we start having hundreds of routers in our network. That means that all these 100 routers will test connectivity and then broadcast the information. So it starts to get a lot of information that is broadcast in the network about just the status of the network. And that can, at some stage, it will be a problem because we have just too much information passed on the network. So what we do then is that we can divide our administrator system into what we call areas. So we make smaller areas. Really what we do is the same idea as we do on internet as a whole, where we split up it in these administrator systems. We now say that, okay, we have such a big network, but we split it up in areas. And then we can route within an area and among areas. So link status information is only propagated within an area. So when we broadcast the information about a current situation, it's only broadcasted within an area. We don't send it to all the other parts of a network. And then routes are summarized within the area before we propagate that information to other areas. So we are limiting the amount of information that need to be passed on. The only cost here is that we get a slight delay, because first we have to summarize all the information within the area before we can pass it on to the other areas. So it will be a little bit slower, but it will reduce the amount of traffic quite a lot. So that's the idea with areas. When the network grows, our administrator system, we split it into areas. At some stage, it may be that it's starting to get a problem again, because we have so many areas and we're starting to send information between all the areas. And what we can do then is actually we can decide to use BGP within an autonomous system. Then it's often called interior border gateway protocol. It's really the same protocol, but we only use it internally. It's not that many autonomous systems that is using it, but some of the biggest ones are using that for the internal. That means we have border gateway protocol at the top, and then we have, for some autonomous systems, we have border gateway protocol again within them. An alternative to Open Shortest Path First protocol is this intermediate system, or ISIS. It's also quite an old protocol, actually. Initially it was developed by DEC as part of the DECnet standard, which is a standard that is not used anymore, I don't think, anywhere. And DECnet was developed more in the context of the OSI model, the Open System Interconnect, where we have 7 different layers, and it's much more divided up, and there are a lot of protocols developed in this OSI protocol stack. And DECnet was developed at the same time. But even if they used that model, which is an open standard, ISIS was a proprietary protocol, so they only wanted to use it for their own purposes, so as a commercial protocol. So no one else could use it, really. They are quite similar to OSPF, so they both use link state, and they have initially very similar properties. What have happened then is, well, as I said, ISIS was proprietary. No one could use it unless they paid for it, while OSPF was an open standard, which was the reason for why OSPF was used much more, because everyone else except DEC could use it without paying for it. OSPF was already originally designed to run over IP, while ISIS which was then connected to this OSI model, was designed to run over something called CLSN, which was part of its OSI protocol stack. OSPF was then used for IP version 4 routes, of course, so it would connect to also run over IP, while ISIS was used for other OSI protocols. The effect of this was that most were using OSPF, while very few was using ISIS. What happened then is that when you use a protocol for a long time, what happens? Well, you see there are things that could be improved in the protocol. You see new use cases, you see new needs emerging from certain type of applications on. And how do you meet that? Well, you meet that typically by extending your standard. You add in new things to handle other situations. And that is what happened with OSPF. It was used for a long time in many different situations, and to handle that, they had to add things to a standard. So OSPF was growing over time, and a growing protocol had benefits but also some disadvantages, because it starts to get heavy to run on hardware. At the same time here, DEC was dissolved, and the ownership over ISIS was turned over to open use instead. And now that OSPF has started to be quite a heavy protocol, people start to look at ISIS again and say, well, it mainly uses doing the same thing, but it's much more lightweight, it's much more efficient if you don't need all of these extra things that OSPF has now. So as a result of that, and also of course that they did some development to ISIS to support IP, for instance, which was of course needed in order to work on internet. So now ISIS is quite popular again. And if we compare these three protocols we looked at, RIP, OSPF and ISIS, RIP is typically only used for very small networks because it doesn't grow very well. OSPF and ISIS are used for bigger networks, and it's really up to the users or the owners of a network which they prefer, but both are used. OSPF may scale better for really big networks, but ISIS typically is performing better in a little bit smaller networks. So the effect of all of these protocols could look like this now then. Here we have 4 different autonomous systems. We have, down to the left, we have a small autonomous system that is using RIP. Above that we have a really big one, which actually use interior border gateway protocol as internal. And then it have sub parts that uses different protocols as the RIP and OSPF. Then we have a third one up to right here, which using OSPF but divided into areas. And then we have a fourth one that is only using OSPF, or it could have used ISIS, doesn't matter. So they all different autonomous system. How things are handled internally is really up to the owner. Doesn't matter. The important thing is that all of them are connected to each other using the border gateway protocol. That is how we can get traffic flowing between them. Problems that could occur with routing. Well, we think of routing, perhaps we see that we have a network, and what we create in that network is a stream of data packets. And those data packets are sent out through our network, and they are going to different places. So we can see it as a flow, but it doesn't work like water flowing, because water is always splitting up and finding the best path for each little stream. If you look at data, typically when we create a flow, all data will follow the same flow, because that is what our routing table says. To send to a certain part of it, we should send it this way. Even if there are possible multiple paths available, we only use one at a time. So multipath routing is difficult. There are some attempts to implement multipath routing. We can say that, okay, when we get a packet, and that packet should be sent to a certain network, we have two entries instead in routing table. And we say that in 75% of the time we send on that way, and in 25% of the time we use another way. That would be a way to spread out the performance of several paths. And there are some initiative to do multipath routing, but it's not much used actually. So we'll send all the traffic on the same way, even if there are other ways. And then suddenly we change for some reason, and then all traffic will flow the new way instead. Fewest hops may not always be the best path. That is something that we need to think about, because often we use hop count as an easy way. The fewer the hops, the better. But one of these hops could be a very, very bad connection. And then it might be better to actually go several hops around it, which are faster. If that is something that we can use, depends of course how we handle routing. If we use hop count and use RIP, we couldn't see this. We will always choose the shortest path, even if it's not the best. If we use OSPF, then we can decide to use bandwidth as a metric, and then we could choose the best path that is longer but faster. But if we scale up to network internet level, we see that we use BGP, and BGP doesn't have a metric at all. So BGP doesn't see this problem at all. It sees that we have a working path, fine. We are satisfied with that. We have found a path. So what is the best path, we can never really see with BGP. Congestion is a problem that you talked about. We have lots of traffic in the part of a network. And with lots of traffic, what happens is that we start building up buffers. Because we're trying to send a packet, but the network is not available right now, so we have to store it. And then we want to send another one, we have to store it. We are building up buffers, and as soon as the network is available, we send something, but it's always full more or less. So that's congestion. Of course, we would like to avoid part of a network that is congested and try to find another way that is not congested. But it's not easy to find that, because congestion doesn't mean that we couldn't reach the destination through that network. It's just slow or slower than before. If we lost connection, we can easily see it, but the congested network is not easy to see. And it can cause at least these out-of-order packets. We send some packets through the congestion and some around it. The ones that go around it reaches the destination much faster. So now suddenly we have packets that arrive before other packets that are sent earlier. And depending on our application, that may be a problem. If we have a data stream, for instance, we're looking at Netflix. Of course, we don't want to see a scene that is coming later, before. So we need to have a packets in order, really, to be useful. Route flapping is also something that can happen here. We find that part of a network is congested, we avoid it, and then suddenly it's not congested anymore, so we go back. And then it's congested, so we avoid it. So we flap back and forth. And just flapping back and forth causes a lot of work and is again not very efficient. We can also have problems with loops in the network. And the worst is if we have a real circular loop. We send to router, that router passes on to another router, and it passes on, and eventually it comes back to the first router again. And then the router looks at this packet, okay, this packet should be sent to that, so we just pass it on, another loop around the network, and just loops around. What happens with a packet that loops around? For how long will it loop around?
Isn't it time to live? Something?
Exactly, time to live. Where do we have time to live? It's a field.
That the package arrives destination.
Sorry?
To make sure the package arrives to destination.
No, not really. The time to live is a field in one of the headers. Which header? It's in the IP version 4 header. We have this time to live field. And what we're talking about here are datagrams, IP packets, right? So that's what we're sending. So that means time to live has an influence. What happens with time to live? When is time to live changed? Each hop, yeah. Each time we arrive to a router, we decrease the time to live one step before we pass it on. Which means that if we have a loop, of course, the loop consists of a number of routers, so eventually time to live will reach 0, and we will just discard the packet. And what happens then? Well, if we use TCP will notice, okay, this packet is lost, so we have to create a new one later on. And then that will be sent around until that dies. So the loop will cause a lot of traffic. And of course, we won't reach the destination. And this is, of course, an error. We shouldn't have a loop. But loops can be caused by what we call good news in quotation. We think that we reach part of a network, but it's actually wrong information. So we are fooled by information from a network, which can cause a loop. We have to make sure that we handle the information correctly. And especially that is if when routes are changing, we may handle that incorrectly. And we can see a simple example of that. Here we have a network and 3 routers. And the idea is that we should be able to reach network N here with the packets. How can we reach network N? Well, initially it's only router A who knows about N, right? So router A can actually send something to network N here. Okay, good news. We have network N available now, and router A can reach it. What happens now? Well, what happens now is, of course, that router A will tell the rest of the network about this news. Regardless if you use distance vector or link state, this news will be spread in the network. And if we use distance vector and probably the RIP protocol, then what will happen is that A will tell B, because they are neighbors, that I can reach network N. Okay? So once they have exchanged information, router B also knows about this. We can reach network N here, and we do it by passing it on to router A. After the next exchange, router C gets the good news. So now anyone connecting to router C can also reach network N here by passing on to B, who in turn passes on to A. And now something happens here. The connection between router A and network N fails. what happens now? Well, what happens now is that in the next exchange here, router A will say that, well, I can't reach network N directly anymore. But at the same time, we get the information from router B who claims that I can reach network N. I have a cost of 2 steps to reach network N here, which is much better than not being able to reach it at all, of course. So after this news here, what happens is that router A will now pass on the traffic to router B, because router B claims that we can reach network N. So now we have a loop here. And if we don't carefully handle this, the only thing that will happen is that in each exchange of routing information, router A and B will think that, well, the cost is increasing all the time. It takes one more step to reach it for each exchange. But we will just continue to be longer and longer away, but in reality, we can't reach it at all. So we'll just pass on information like that. Now, there are, of course, ways to handle this situation. Typically, what we do is we suppress bad news. So if we have a bad news here, instead of saying that, okay, maybe we can go this way to go to B here, we say that we now have lost connection to network N. And then if anyone actually have connection to network N, we have to get that through the normal exchanges. So as soon as something is lost, we just say that we can't reach it anymore. So that is what we call backflow here, which we'll actually call a loop. And to eliminate that, we lock down changes that are worse. Good news is always delivered, but bad news is always turned into not reachable. There are other routing problems as well. We have something called a black hole in the network. A black hole means that we send to some part of the network thinking it will actually be delivered, but they're just silently dropped. We don't see that they are dropped, we don't get any indication they are dropped, but they are dropped. We couldn't reach the destination. That can be caused by routing packets that are lost, which of course can happen. I mean, routing packets, just like any other packet, they can be lost. And we have this route flapping that we already talked about, that we continuously are changing between 2 possible paths, causing a lot of work, and that typically a lot of packets will be delivered out of order as well. So that is a problem that we also would like to try to avoid. So there are problems with routing that is not obvious how to handle, but we need to think about them. And then we have a further problem, and that is the overhead of the routing itself. Because in order to do routing, we need to send information on the network, of course. We already said that the RIP protocol have this problem because we are sending this entire table. And we said that open shortest path, when it grows, even if we're only sending the link status, with big network, it still causes quite a lot of traffic. That's why we divide it into areas. So the question is, how much overhead will our routing protocol give us, and how can we handle that problem? Well, of course, what we can do is decrease the frequency of how often we share information. The longer time between it, the less overhead it will be. But, of course, at a cost, because then changes in the network will take longer for us to notice, which means that during that time, we will not route efficiently, or we may not be able to route at all. So typically, we want to have quite often that we change information, but it shouldn't affect the overhead too much. If you look at RIP, for instance, the default state is every 30 seconds that we change information. For other protocols, we can often change how often they exchange information, so we can work with that a little bit if we want to. So this is for normal routing that we talked so far. And in normal routing, we always have a sender who creates a packet, and that packet should go through a number of networks, a number of routers, and eventually be delivered to a destination. But we also have other types of traffic in the network. We have multicasting. With multicasting, we have one sender, but that packet should be delivered to several destinations. And we have multicasting, for instance, on a local network. In Ethernet, we have that possibility. That is on a physical level. We can have a multicast Ethernet address, and that will be delivered to anyone that listens to that multicast address on Ethernet. We have broadcasting the same way, that we can send to everyone on the Ethernet. On that level, it's easy because it's a physical network. Whenever we send a packet, it will be available in the entire network, and who listens to that or not is easy to configure in each node. But if we scale this up to internet, it's another thing. Because now we have a computer somewhere in the world create a packet that should be delivered to one computer here in Kalmar, one in Stockholm, one in Hawaii, and then to 10,000 computers in Alaska for some reason. How can we make sure that the delivery of those packets are efficiently done on internet? But that's what we need to support if we support multicast routing. For IP version 4, we have this class D in the original classful networks that have a number of addresses allocated for multicasting, so it is part of IP version 4. And for IP version 6, again, it's part of the IP version 6 address space. So multicasting is something that is intended to be supported on internet. So let's look at this problem a little bit. We have a multicast group, then, that's what we call it. And a multicast group is everyone that listens to a certain IP address then. That is a group. Now, anyone can join a group at any time. I can decide I want to listen to any sendings to that multicast address. How do I inform anyone that I want to do that? Well, what I do is then I will use this protocol called Igmp, Internet Group Multicast Protocol, to tell my nearest router that I would now like to have all packets that are sent to this multicast address. I want to have them delivered to me as well. So Igmp is used between a local host and the local router to tell the local router that I would like to have those packets. And now it's up to the router to solve this problem, to make sure that all packets sent to this multicast address, wherever they are sent in the world, actually arrive to my computer. So anyone can join, anyone can leave a cast at any time, which means that now we should stop of sending, of course. And to make it even more complex, any computer can send to this group. They don't even have to be a member of a group. Anyone can send to a multicast group anyway, and it should be delivered to anyone that is subscribing to that group. So it's not an easy problem. How can we solve it? Well, we could solve it by broadcasting everything on internet. That would make sure that whenever I send something, it will be available to everyone, everywhere. But of course that would be impossible. It would flood the internet directly with too much traffic. So we couldn't do that. We have to be smarter than that. But how do we know when a packet actually have to be forwarded to a certain net or not? Well, if we start with the easy part here, the Igmp. Here we have our local router, the multicast router here. We have what we call a video client. And when that video client now would like to take part in this video stream, that is assigned to multicast address. We, with this Igmp protocol, we send a packet to our local router and say, now I would like to have that information as well. As you see, there could be a switch on the way here between my host and the router who is looking at that traffic. So we can actually have filtering on level 2 here with a switch, so they can be Igmp aware. They are listening to this traffic and see, okay, there is a certain host here. Because as you know, switches can filter traffic, which means that they also need to be aware that this host wants to have access to traffic to this IP address. But now we have a bigger problem then, because now we have our local multicast router here who need to communicate with other routers in the world about, okay, now I have a client here would like to listen to this. And to do that, we use what we call, as you see, a PIM here, a PIM protocol, in order to tell the world that I have a client here. So let's look at that PIM. What is that? Well, I think we can skip that one actually. I think we skip that one. It's easy. You can read that on your own. That PIM protocol is then a multicast routing protocol. And to accommodate membership to that, we need to somehow tell the world that this host would like to listen to this traffic. And there are a number of different protocols developed actually to try to handle this problem of group membership here. And they are divided into these 3 different types here: flood and pruning, configuration tunneling, and core-based. So let's look at each of them separately. The flood and prune is the simplest one, and it works good in a limited network environment. So the idea with flood and prune is that we actually do broadcasting all traffic. As soon as it's a multicast, we actually broadcast it instead. And then we see actually all the routers know about this, and since all the routers receive information about hosts that would like to take part in the multicast group or not, they know if that packets actually have to be forwarded to that part of the network or not. So we start with sending everything, and then each router has a task to block traffic that doesn't have to be forwarded. And they know what doesn't have to be forwarded from the Igmp protocol. So this works quite well in a small network where we only have to, anyone can send and everything will be broadcasted, but it will be pruned away, it will be filtered away, so we don't send it to parts of the network that doesn't need it. But when the network grows, we have to find other solutions. And the configuration and tunneling then mode is working well in situations, as you see, where we have a group of people that are in some specific places. But it's not anywhere in the world. It's more that we have a few possible locations where people are using this multicast group. So what we do then is that within each of these locations, we use more or less the flood and pruning technique. But in order to reach other parts, other sites, we do the tunneling part instead. So when someone is sending a packet in one of these sites to this multicast address, first is flooded within that site, and then one of the routers in that site encapsulate it into a normal unicast packet and send it to routers in the other sites. And in these sites, it's packed up and again broadcasted within those sites. So this works well if we have a few sites that we can pinpoint and we have quite a lot of users in those sites. But the last idea is then the core-based discovery. If neither of these works very well, core-based is the last idea then. So this works if we have a larger network and we have people here and there, and it's relatively dynamic where they are located, then core-based discovery is working best. What we do is we start by allocating a core, and the core is really one router, and we can reach that router with a unicast address, so it's normal traffic. So whenever we want to send something to this broadcast, we actually send it as unicast to the core. In the core, then we know there are a number of other routers who also would like to take part, so we pass it on to them. And then it's built up as a tree, so we continue to pass on traffic using unicast until we reach the end networks, where again we'll use broadcast to reach all the hosts in that one. And whenever someone new occurs that would like to be part of a unicast or a multicast address, it has to create a new link to this tree that we have. So it has to link up to one of the routers that already are part of this tree here. So we get a big tree structure and with one core that is always in the center. Of course, it's a bit vulnerable for attacks then, because if a core is not reached, the entire multicast group will fail. So it's very dependent on the core here. So again, this is third type, and it works relatively well for bigger networks, but it doesn't work very well for entire internet. And actually, if you look at the situation today, we don't have multicast routing throughout the internet. We have parts of internet that decide, okay, we would like to build up multicast access in our part of internet. And all the routers in that part of the network support one or of these protocols then in order to support multicasting. But there is not any uniform solution for the entire internet. In Europe, we have something called MBone, for instance, which is an initiative on EU level to set up multicast within Europe. So there are a lot of research networks in Europe that is connecting to MBone, but it doesn't reach all the people in these countries. It's only the research networks that are connected. So again, it's limited, but that is one of the biggest in the world that is known. If you look at your home, for instance, you may have streaming. You have maybe Netflix or something like that you are streaming to your home. That could potentially be solved with a multicast stream, because that is typically a good situation. You have one video stream, especially if it's live streaming then. We send one stream and it will be forwarded to a lot of people listening to it at the same time. Instead of creating different streams for each one, we just create one stream. So that would be a good application for it. But typically, if you look at how it's sold today in networks, you don't use multicast routing at this level. Instead, you use actually at a much lower level, use what's called MPLS routing, that is on the link layer rather than on the network layer. So it's a very complex problem, and there are different solutions for different types of networks, but there is, as I said, no solution for the entire internet, unfortunately. Right, I think we can already talked about most of that. Yeah, so there are a number of protocols then that are one of these three. We have distance vector multicast routing, core-based tree, protocol independent multicast. There is one called sparse mode, one dense mode. There is one multicast extension on open short path. Quite a few of them. All of them are one of these types, what we talked about already, but none of them are working internet-wide because it's too big a problem to deal with it. So multicast is always within smaller networks still. May change in the future, but we don't see it right now. Right. Any questions before we stop for today? Do we have any questions in the Slack channel? No? Okay. So on Monday there will be a lecture from Växjö instead, and we'll talk about network performance and quality of service. And then we continue from that. But keep your eyes open for the fourth assignment. Some details will be published this week and the rest next week probably. Okay, thank you for today.